That's right. We don't have any discernible differences in the solution. Okay? There's nothing that is different throughout the whole solution. So top, bottom, left, right, wherever you take a sample of this solution, it should be the same. Right? The dissolved substance is completely dispersed throughout the solution. Concentration is the same. Usually when we talk about solutions, we talk about a solid being dissolved in a liquid. Right? And what's usually the liquid it's being dissolved in? Water, right? Water is what we call the universal solvent. Okay, I'll give you those terms here in a second. But some liquids can dissolve into another. Generally, we think of that more of a mixture, and that's okay. Solutions are still homogeneous mixtures, so as long as they mix uniformly, then that's okay. Some gases can be dissolved in liquids. Can you give me an example of when that happens? There's one really common example of when a gas is dissolved in a liquid. Maybe. Are you thinking like liquid nitrogen? Or... Right. Okay, I see what you're saying. Okay, yes. This one is more of something like an everyday product. No. Yeah, in what?
Soda.
When I open a pop, it goes shh, right? That's just those bubbles coming to the top. So while that item is sealed, those carbon dioxide molecules are dispersed throughout the liquid, right? They're dispersed throughout that solution. So by the time you leave your pop open too long, what happens? It gets flat because what happened to all those carbon dioxide molecules? They're no longer incorporated in the solution anymore, right? They work their way to the top and they're out.
If you could drink a soda that never was opened, it'd be really fun.
Okay, so we call water kind of the universal solvent because it's what we use for most solutions. And when we talk about a solute's solubility values, it's about how much can be dissolved in usually 100 mils of water. That's kind of the standard benchmark that we make. I'm going to demo how to make a solution probably next class. We're going to do a solution and a dilution next class. But do you know what this piece of glassware is called? Price is Right style? No? A volumetric flask. This is called a volumetric flask. It only has one single marking on it. Right? It has a single marking on the neck of that volumetric flask, and that's because it's only measured for one specific volume. This one's 100 mils. So when I make a solution, I don't make it in a graduated cylinder. I don't make it in an Erlenmeyer flask. I don't make it in a beaker. I make it in a volumetric flask because I know the exact volume here. Why do you think it has the skinny neck?
So you can have a more precise...
Right, I'm more precise. It would be really hard to read a water level if I tried to measure it on that wide of a base, right? But a volumetric flask has a skinny neck. We fill it, we mix it up, and then we start adding water drop by drop until we get to the line. If we go over the line, we start over.
Oh, God.
You can't just dump it out, right? You have to start over. So you're really, really, really precise when you make solutions using a volumetric flask. Okay, so we'll go through that next class, how to make a solution and dilution. The lab we're going to do is going to require quite a few different lab techniques for us. So really, but the day before we do the lab, we're going to spend some time in the lab practicing with this water, using the pipette correctly, using the flask correctly, reading the burette correctly. So we're going to do a bunch of that stuff in the lab, and we'll practice with solutions then. Okay. All right, which one's the solute?
The Kool-Aid.
Yeah, most common one. Okay. Blah, blah, blah. We already talked about this solute solvent. Water is what we call a polar molecule. Can anyone remember what it means to be a polar molecule? Polarity within the molecular geometry of a molecule means that the electrons are not distributed evenly throughout the molecule. Okay? So what this means, in a water molecule, in a water molecule, my formula looks something like this, or my molecule looks like this. Boom, 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 boom. Okay? And all my electrons are found in this region, right? Even the electrons in the bonds are pointing toward oxygen. Right? So these electrons are pulled toward the top of the molecule, and that's what we consider a polar molecule, when our electrons are not distributed evenly. And so that means, since water is polar, it dissolves other molecules that are polar. It doesn't dissolve non-polar molecules. If we use this term, like dissolves like. So polar molecules dissolve in polar polar solvents, non-polar solutes dissolve in non-polar solvents. Okay? All right. This is important right here. When ionic compounds, most oftenly they're called salts. Sodium chloride is just one type of salt, but it just gets the name for some reason, right? When ionic compounds are put into water, they dissolve by breaking into their individual ions. That's called ionization, right? When we talk about ionization, that means it is becoming two individual ions.
So like ionized like pills, right?
Right, so ionized things means just that we're dealing with it by themselves. So when we put NaCl into water, really we're going to end up with a sodium ion and a chloride ion, right? And then water molecules surround those individual ions and cause them to disperse, right? A water molecule has partial positives and partial negatives on that molecule, and it will start to pull and attract to the correct charge. Okay, and we'll kind of see what that looks like here in a little bit. Okay, I want you to watch this quick video on the dissolution or the dissolving of a solid in a liquid. You think it's playing? I don't.
But isn't salt water like, does the salt go to the bottom?
If there's too much of it, if it's what we call supersaturated, right? If there's not enough water to support all that.
Or am I thinking sugar?
Same thing, both of them.
I don't know.
Okay, this is supposed to be a video, but it's not, so that's cool. But what it shows is that this molecule, right, this is a block of salt molecules, and these are all of these little red and whites, they're all water molecules, and they come and just pick off ions one by one, right? They pick off ions just one by one. They surround one of them and float away, surround the other one and float away, and then eventually it's all dispersed throughout the solution evenly. Okay, so sorry, there's supposed to be a little video there. All right. The first step in the solution process requires energy. So to start the dissolving process, we have to put energy in. You don't have to write this part down. Just think about this. Name 2 ways to encourage the dissolving of a solute. Think about it with the person next to you. Come up with a couple ways that we can encourage. If I want something to dissolve, how can I make that happen? Okay, think about it, people next to you. All right, so I'm hearing one right off the bat. What is it? Heat, right? When I heat things up, why would that encourage the dissolving process? Think about it on the molecular level. What happens when I add heat? Yeah, the molecules get excited and they move faster, 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 and they bump into things more often. And if the water molecules are bumping into these ions faster, they're going to be moving faster, right? That's the basis of it. And second thing is when those when the bonds between those when the bonds between the salt particles start to move faster with energy, that causes a break as well. And so it causes that to move faster. And second thing, what was another one? Heat causes the dissolving process to go faster. Stir it, good. This does the same thing. It makes the particles come in contact more often, which encourages the dissolving process. What else? What about physical manipulation of the solute?
I like salt bay in it.
Well, okay, what does that mean? Just like sprinkling it in?
Yeah.
Okay. Yes. I'm thinking of when you get the frozen concentrate of orange juice out of the freezer. You know what I'm talking about?
Yeah.
Dump it into the water pitcher. How does that go? It takes a while. If you were going to stir it, it was going to take a while, right? You do better to cut it into smaller pieces, grind it up, mash it up, whatever. Get that stuff separated first so that you have more surface area for water molecules to come in and pick those ions off. Does that make sense? Right? So physical manipulation of your solute can make a difference. That's also why they don't give you Kool-Aid in a block, right? They give it to you in a powder. You know what I'm saying? Those things make it go faster. All right, lots of other ways we can do that, but those are 2 big ones. All right, so this is what we were talking about when we said solubility. Solubility is a given value. Okay, it's a numerical value assigned to different particles based on how many grams of solute can be dissolved in 100 grams of water. okay, or 100 milliliters of water. Usually they're given at a certain temperature, usually 25 degrees Celsius, because that's room temperature. So the solubility value for compounds might say it's 23 grams per 100 mils or whatever.
I never understood room temperature because, like, this room seems hot.
Right. Room temperature is just an assigned value of 25 degrees Celsius.
What is it in Fahrenheit?
I don't know what the conversion would be in Fahrenheit. I don't know, somewhere in the low 70s probably. I don't know exactly. I don't know what the conversion is on my head, but room temperature is generally 25 degrees Celsius. But solubility charts will always be given at that temperature because we know that temperature affects the solubility of solids within a liquid. All right. So that's what solubility means, right? The ability of a solute to be dissolved. 77, thank you. All right, I don't need you to necessarily write this part down. I just want you to kind of listen and think through these things. So we're going to look at how temperature affects the solubility of certain things. Temperature increases the solubility of solids and liquids, right? Would you agree with that? That's what we talked about. When things get hot, our solubility increases, so it dissolves better. But in gases, solubility decreases with temperature. That's the example we saw with our pop, right? If we leave it in the car and it gets hot, we open it up and it's flat, right? Most of the time it's flat. Those carbon dioxide molecules have moved their way out of the liquid and no longer has that fizz, right? The bubbles. Gas escapes to the atmosphere with increased energy. So that's what we talked about with our pop example. So how does pressure affect solubility? It doesn't really make a difference when we're dealing with solids and liquids, but it does affect the solubility of gas. Solubility increases with pressure, right? The solubility of a gas and a liquid increases. As we smush those molecules closer together, basically it forces the gas molecules to get in between.
So, like, in, like, higher up altitudes, there wouldn't be as much of a pop when you open up a soda?
Right.
Okay.
Right. And second thing, when we say pressure doesn't have much effect on solids and liquids, that's not really it's a fair statement, but you also need to think about generally when we increase pressure, we increase temperature as well, right? Generally, when there's an increase in pressure, our molecules are moving faster and faster and faster, which is also an increase in temperature. So there's kind of a relationship there, but it technically is independent of pressure. All right, now we're going to get to the good stuff for today. We're going to talk about, let me make sure I didn't skip something. Like dissolves like. We talked about that a little bit. Okay, yeah, that's good. All right, now we're going to get to what I wanted to get to today, which is molarity, and this is how we measure the concentration of a liquid, okay, or concentration of a solution. Okay, molarity is given with a big M right here. Big M is the unit for molarity, and you need to have this equation down. It's moles of solute divided by liters of total solution. So moles per liter. Okay? We're going to use this equation a lot. You're going to need your periodic table out as well as your calculator because we're going to have to do some calculations to get to moles. Okay? This is, I think, one of the only problems I don't have printed out for you. So go ahead and get your periodic table out. If you want to start writing down this question, you can. But we'll work through this one together. So we're going to go moles of solute, which our solute is our sugar. Sorry. All right, so 4 grams. And I told you that the formula for sugar is right here. So go ahead and find molar mass of that formula.
That's a lot.
It should be pretty big.
270. That's how many grams?
270 grams, right? That's what I had as well.
And then you divide the 4 by that.
So 270 grams is equal to 1 mole. And then I just plug that in. 4 divided by that. So I get 0.0148148 moles. Right, I don't care where you take that. 0.0148 moles. And so now I'm going to have molarity equals 0.0148 moles divided by, we got to put that in liters, 0.350. And so my molarity comes out to be 0.0423. And you just leave it as, the unit for it even is just capital M. Okay, so both the variable and the unit are just big M.
That was my nickname in middle school.
Okay.
Big M.
What's the concentration in capital M? So I'm gonna mostly tell you that it's molarity. There's another one that's called molality, and that's another way to measure concentration. But it's a little m, so it's different. But what's the concentration in molarity of a solution mixing 10 grams of H2SO4 with enough water to make 100 ml solution? So this is important. This is the total volume of our solution. That's important. This is 10 grams. We're going to convert that to moles.
Is it sulfuric acid?
Right. Okay, the way you read this final answer is you say it has a concentration of 1.02 molar. Okay, 1.02 molar. So in this problem we're given how many liters of a 3.4 molar isopropyl solution can be made with 78 grams. So in this example, we're given 3.4 molar equals equals some number of moles, which we can solve for over liters. Right? Our moles, we can solve by going 78 grams, 36 plus 8 plus 16, so 60. Is that what we had for our molar mass? Okay. 1.3 moles is how many moles we started with, so I'm going to bring that back here. And then do you remember our kind of trick for if we have this triangle type solution or triangle type equation?
You can do
You just
1.3 and 3.
1 over 1.
So let's just
Switch the M and the L.
right. I switched these two places because I need to get L by itself. So times L, divide by 3.4, divide by 3.4. So what that ends up looking like is I just switch those two places. So it ends up with liters equals 1.3 moles divided by 3.4 molar.
Would that be
No, what's that unit? 0.382 liters. Okay. So if we wanted to put it back in milliliters, we'd go 382, but not necessary. Because it doesn't say, oh, it actually says how many liters, so we want it to be in liters. Molarity is always moles per liter. So that should always come out in liters. Okay? Almost morality. All right. Try this one on your own. How many grams of potassium phosphate would be needed to make a 1.32 molar solution in a container that holds 4.2 liters? So now you need to solve for moles, then convert it to grams. I'm about to do it right now. Oh, sorry. You already have it printed. I got it. Yeah.
You want to check my checks and what did you get? What'd you get? What did you get? 45 or 41.54.
I didn't even get anywhere close to that.
Oh gosh.
Mine's really good.
What? Yeah, I got 1,000.
K3.
What did you get?
Dummy. Oh my goodness.
Come on.
I got basically that. 1,175.
It's K3.
Did you just put 5.5?
5.5.
I got 5.54.
Yeah, I went too far.
5.544 moles when I multiplied those two together.
And then I got
You multiply, not divide.
Yeah.
Because if we want to get moles by itself, all we need to do is
And then I got
get rid of
2, 1, 2,
4.2.
3.
Right, and then we multiply by on that side.
Oh, I didn't.
It's when the variable's in the bottom that we do the switch.
Well, because K is 0.3 or 0.1, so then times 3.
I kept it at 39, but yes, you could. You're right. You could keep it at. Okay, are we somewhere in the ballpark there? Moles. To find moles, we just multiplied these two together, right? Because if I want to get moles by itself, I just have to multiply by 4.2. And it cancels. Multiply by 4.2, and that's what I got there. Then I converted to grams. Okay, very good. So what we've been doing now is moles of the total object, finding the concentration of the total compound. Now we're going to look at finding the concentrations of the ions individually. Okay, so we're going to use our molarity to be able to calculate the concentration of individual ions within a solution. So give the concentration of each ion in the following solution: 0.5 molar cobalt 2 nitrate, right? So when this thing ionizes, it would split into a cobalt. Man, I keep forgetting to hit my pen here. Okay. It would split into 1 cobalt, and then it would split into 2 nitrates. Agreed? Oops. Does that part make sense? Because of that right there. So if this thing ionizes, it's going to split into a cobalt and 2 nitrates. So if my concentration of the entire solute, or my entire compound, is 0.5 molar, that means I'm going to have 0.5 molar concentration of cobalt, but what would my concentration of nitrate be?
0.25.
Wrong. Backwards. 1.00 molar. Right? Because I have twice as much nitrate as I do cobalt. Does that make sense? Like, let's say that I put this 0.50 molar. Let's say I had a liter of all of them. Right? I have 2 moles of nitrate. I have 2 moles of nitrate there. And so that means I would end up with, sorry, I'm not solving for anything. That's confusing. Okay, if I have 0.5 molar and I am dealing with 1 liter, I would have 0.5 moles of cobalt. And so then I have to look at the ratio between cobalt and nitrate. And I've got twice as much NO3, which means I'd have 1.00 moles of NO3 minus 1. Right? So it's really, we can solve it the same way, and then we look at what's the ratio between these ions. And in this case, we needed we're going to end up with twice as many nitrate as we do cobalt. Okay? So let's look at a problem here. Give the concentration of each ion in the following solution. 1 molar iron chlorate. What do the ions break into, and what are the mole ratios? So let's look at it. When this ionizes, I'll end up with an iron. And what will its charge be?
3.
Plus 3. And then I will end up with a ClO4 minus 1, right? But how many of those will I end up with?
3.
3 of them. So that means iron's concentration is still 1.0 molar. But what's the concentration of ClO4 minus 1?
3.0 molar.
3.0 molar. Right? Because I would have, if I was dealing with 1 mole of this compound, I'd end up with 1 mole of iron atoms, but I'd have 3 mole of chlorate molecules. Right? Ions. Does that make sense, the ratio there? That's all we're doing here. Looking at our ratios of the ions themselves. All right. Give the constant, oh no, not wrong. Calculate the number of moles of Cl minus 1 ions in 1.75 liters of that molar zinc Cl2. Okay. Go ahead and try this one. first thing we want to do is just find the number of moles. So we've got 1 times 10 to the negative 3 molar equals moles per 1.75 liters. Okay, and so we solve for it. How many moles of the total substance do we have? 1 times 10. Right. So that means I'm left with 0.00175 moles of ZnCl2. Okay, and so if I'm just looking at moles of chlorine compared to that, if it helps you to put it into like our chart ratios, we could say 1 mole of ZnCl2 is 2 moles of Cl minus. Right? If it helps you to see it that way, you can do it like that too, right? If we look at just this compound, 1 mole of this would mean that I have 2 moles of this based on that subscript. 2 moles of just chlorine. So if it helps you to run it through the chart, you can do it that way as well. Right? So I'm going to go 0.00175, multiply that by 2, and that means I've got 0.0035 moles of Cl minus ions. Okay. Because for every mole of zinc chloride, right, for every one of these molecules, there's 2 chlorines, right? There's 1 zinc and 2 chlorines. And so this is my concentration or my moles of the whole substance. And so if I've got 1 mole of the whole substance, I would have 2 moles of chlorine. So if I've got this many moles, I'd have to have twice as much moles of chlorine. All right, that's just how it works out.
So if it asks for zinc?
If it asked for zinc, it would have just been this, because it would have a 1-to-1 ratio. Good question. Okay.
Wait, so why wouldn't it just one zinc?
If it was just zinc, zinc only has 1 molecule in 1 atom in that compound. So if there was 1 mole of it, 1 mole of the compound, there'd be 1 mole of zinc atoms. Okay. All right, try this one. This is the last one we're going to do today.
So you gotta convert it to grams.
We need to convert that to grams, then to moles. This is not dealing with ions. This is just a molarity problem. What'd you say? Yeah, quickly. Make sure you see this is 0.14 molar.
Oh, what am I doing? I'm just an idiot. Right? I'll be honest, where did you get 1.71?
This was the result from when I calculated moles. I just didn't write it up there. 1.7 times 10 to the negative fifth. Right, when I calculated the moles of sodium chloride present, then I ended up with 1.71 times 10 to the negative fifth. And then from here, this was the type of equation that we switched the spots. So I did 1.71 times 10 to the fifth divided by 0.14, and I get 1.22 times 10 to the negative fourth liters. And so you could have called it 0.12 milliliters if you wanted to, but either 0.122, you could have called it either one of those. Right? Both are correct. Right, so in 0.122 milliliters of blood, there would be 1 milligram of salt.